So the question was posed to me. Somebody asked, they were doing a finite element simulation where they had a piezoelectric disc and they were applying a force and they wanted to generate a voltage, and the equations were pretty simple, not complicated. You can use the piezoelectric G coefficient to calculate the electric field generated from a force on a disc or a piezo element, or you could just do it the raw, the kind of the more raw way where you use force and you use that to calculate charge through the piezoelectric charge coefficient. And so it's a simple thing that somebody should probably be able to achieve. Like you apply force, you get a voltage. And they were using this and doing this thing in FEA as well, and they got a significantly lower voltage when they applied a force in FEA versus that in kind of hand calculations. So what was the difference here? Why did they get a lower voltage? And maybe we think that, hey, the material constants may have been wrong. Well, those material constants that you put in FEA, FEA is an ideal sort of simulation platform as long as you have enough nodes now. It's a more ideal linear theory. So that's what the constitutive equations, that's what the piezo constants are all about, linearity. But so what's the difference was why the voltage was so low was because the person doing the simulation, the engineer, used fixed boundary conditions on the bottom of the disk and then applied the force. So what? You need fixed boundary conditions in order for static finite element analysis to work and run. So you have to apply it. So they fixed the bottom of the disk and they applied a force, and they expected the voltage that they would get from the G coefficient or other methods of calculating that. However, there is something inherently wrong in that assumption. Boundary conditions they're just extremely important to take into consideration. So when the disk was sort of fixed, what does fixing mean? Fixing doesn't mean simply supported. Your static simulation won't work if you just simply support an object. So what happens if you fix that the disk, when you apply a force to a material, it stretches out. It compresses in the direction that you apply the force, but it stretches out doing the Poisson's ratio to some amount of volume conservation that the material will attempt to achieve. So it'll actually get wider around the edges. However, you fix that boundary condition on the bottom, and it will then resist that outward motion, that outward kind of flow of material that kind of goes outward. It will resist that. And that resistance actually stiffens up your disk, and it causes a lower amount of displacement to occur in the thickness. So in effect, you added another constraining equation, not allowing, because that force to voltage conversion, it assumes something about the stiffness. It assumes something about how much strain will happen in the material as a result of applying that force, and hence it's going to generate that charge, which is related to the piezoelectric charge coefficient D. So because that fixed boundary condition was actually constraining, and in real life, if you test a piezo device, you have it, piezo disc, you have it sitting on a piece of foam or like a surface. That surface is likely not going to constrain and really hold tightly to that disc as it's moving outward when you apply that force. There's going to be some wiggle room. There's going to be some movement. Even if you apply epoxy, there'll still be some movement of the disc. It won't be that perfectly bonded condition. So we just understood that perfectly bonded conditions don't really work all that well when you're doing finite element simulations. So in a lot of our simulations, we use fixed. So we work in the static mode. Like it's a low frequency operation. There's a static kind of deflection which is occurring, and so in that case, we're simulating a preload perhaps. So it's a pure static kind of situation. So how do we simulate in that case? So we got to remember and kind of take a step back that what is static exactly? Static is really, 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 really low frequency. It's a frequency of 0 hertz. That's kind of static. And instead of simulating with that low frequency of 0 hertz, or in terms of a static simulation where you need a fixed boundary condition, you can actually simulate with 10 hertz, 1 hertz, 1 kilohertz. You apply a force on the top and a force on the bottom of your piezo to kind of kind of keep that pressure internally constant, have that supported. And now you will, if you do a harmonic analysis, you will no longer have the need to have a fixed boundary condition. If you do harmonic analysis, you don't have a need to have a fixed boundary condition. Therefore, you will be able to do the simulation without constraining the piezo in a different way. And as well, you can generate that voltage that you calculated from your constitutive equations, from your G coefficient by applying the force. You get the electric field, and then you multiply by the thickness. You would be able to then do that proper calculation. So I hope you enjoyed this video and learned a thing or two about applying boundary conditions for your low frequency piezoelectric analysis. Thank you.